Sometimes you'll get a question where you'll be not given functional equation. Say, for example, you may be given fx plus y is less than equal to fx plus fy, which is subadditive, or maybe this inequality fx plus y by 2 is less than equal to fx plus fy by 2, which is midpoint convex. Now in such questions, there are two pathways. Either you'll get an exact function using sandwich principle, so if you can derive fx is some greater than equal to phi x from one direction, and then from other direction you can derive fx is less than equal to phi x, then from sandwich theorem we can say this fx is exactly phi x. So this is one pathway, and the second pathway is from the inequality you can infer monotonicity or boundedness, which can give you the condition of regularity needed to rule out wide solutions of Hamel basis. Now in this question we are given that if f satisfies fx plus y is less than equal to fx plus fy for all xy, and also fx is less than equal to x for all real x, find this function f. Now from the second condition we can write f0 will be less than or equal to 0, and in this first condition if we put xy as 0 we'll get f0 as greater than equal to 0. That means both the conditions, they can only be true if f0 is 0. Now we'll try and use this. For this first inequality we'll put y as minus x, we'll get f0 will be less than equal to fx plus f minus x, or simply fx plus f minus x will be greater than or equal to 0. Now we can write fx will be greater than or equal to minus of f minus x, and from the second one we can write f minus x will be less than or equal to minus x, or minus f of minus x will be greater than or equal to x. So it will be greater than or equal to x. So we'll get this condition that fx will be greater than or equal to x. But we are given that fx is less than or equal to x. That means the only condition possible here is fx equals x. So the function which satisfies the two given inequality is fx equals x. So here the question is find all f from n to n such that f2 equals to and fmn it is equal to fm into fn for all coprimes mn. So that means GCD of mn, it should be 1, and fm is always less than fn whenever m is less than n. Now if we put m and n as both 1, then we'll get f1 equals f1 square. So either f1 is 0 or f1 is 1, and since codomain is natural numbers, it cannot be 0. So f1 is 1. Now we're given f2 as 2. Now we can write f6 as f2 into f3, and f2 is 2, so it will be 2f3. Now we know that 2 is less than 3, is less than 4, is less than 5, and is less than 6. So f2, which is 2, will be less than f3, and it will be less than f4, which is less than f5, and it will be less than f6, which is 2 times f3. Now there are strictly 3 increasing natural numbers between 2 and 2 times f3. Now this forces f3 equals 3, f4 equals 4, f5 equals 5, and f6 equals 6. So we guess this fk, it must be k for all k belongs to n. Now we prove it using strong induction. So our first case, P1. Now F1 is 1. This is true. Second is Pn be true, or all the cases from P1, P2, Pn, they are true. That is, any Pk will be equal to k when k is less than or equal to n. Now we choose a convenient coprime pair, and we know that 2 consecutive numbers are always coprime. So f n minus 1 into n will be f n minus 1 into fn, which is n minus 1 into n. Now we know that n is less than n plus 1. It is less than n plus 2. And it will be less than n minus 1. Or fn will be less than fn plus 1, fn plus 2. And this is fn into n minus 1. Now fn is n. fn into n minus 1 is n into n minus 1. Now the function before this will be f n square minus n minus 1. So total number of functions in between these two functions will be n square minus 2n minus 1. And if we look at gaps between these two natural numbers, it will be n square minus n, and then minus n minus 1 will also be n square minus 2n minus 1. So for it to be an increasing function, there will be exactly a gap of 1, because more than one gap is not possible in this structure. So from here we can say f n plus 1 will be equal to n plus 1. That means p n plus 1 is true, and therefore from induction we can say f n will be equal to n. Now the question is, let f be a function defined from 1 to infinite to 1 to infinite, satisfying these two conditions. And the first condition is fx is less than equal to 2 1 plus x for all x belongs to its domain. And second condition is x f x plus 1, it is fx square minus 1 for all x belongs to 1 to infinite. Now we need to prove that fx is less than equal to x plus 1. Now from this condition B we can write fx square, it will be x into fx plus 1 plus 1. Now from this first we can write fx plus 1 will be less than 2 into 2 plus x. So it will be less than or equal to x into 2 plus x plus 1, which is 2x square plus 4x plus 1. Now if we add 1 and subtract 1, it will be 2 into x plus 1 whole square. So it will be less than 2 into x plus 1 square. Or we can simply write fx will be less than root 2 x plus 1. Now we'll use this fresh bound. Instead of this a, And again, we'll use this argument. So again, we can write fx square. It is xf x plus 1 plus 1. Now it'll be less than x into, now fx plus 1 it'll be less than root 2 x plus 2 plus 1, which is root 2 x square plus 2 root 2x plus 1. Now we can add root 2 and subtract root 2. So it'll be less than root 2 x plus 1 square, because 1 minus root 2 is a negative number. So from here we'll get another bound. Fx is less than 2 to the power 1 by 4 x plus 1. So if we keep applying these iterations, we'll get fx should be less than 2 to the power 1 by 2 x plus 1. Then we got fx less than 2 to the power 1 by 4 x plus 1. And then we can get fx will be less than 2 to the power 1 upon 2 to the power n x plus 1 for all n belongs to natural numbers. Now, as n increases, 1 upon 2 to the power n, it approaches 0. So clearly this fx will be less than x plus 1, which is what we need to prove in this question. Now the question is, let f be a function defined on R to R such that f3 is 1 for all x belongs to R. F x plus 3 is greater than or equal to f x plus 3, and f x plus 1 is less than or equal to f x plus 1, and says put gx as fx minus x plus 1. We need to find the value of g 2008. Now, from this first equation, we see fx plus 3 minus fx will be greater than or equal to 3. Now, from this second one, we can write fx plus 2 will be less than fx plus 1, which will be less than fx plus 2. And in the same way, fx plus 3 will be less than fx plus 1 plus 2, which is less than fx plus 3. So from this second condition, we'll get this inequality fx plus 3 minus fx is less than or equal to 3. Now, both of them, they can be simultaneously true if and only if fx plus 3 minus fx, it is equal to 3. So this is the equation we have. Now in the question it is given that f3 is 1. And since this is an equality, that means all the conditions given in the question, they'll also hold. So we'll get fx plus 1, it should be equals to fx plus 1. Now we are given gx equals fx minus x plus 1. We can write gx plus 1 as fx plus 1 minus x plus 1 plus 1. Now fx plus 1 is fx plus 1. So it will be this fx plus 1 minus x, and which is nothing but gx. So this function gx, it's periodic with period 1. Now we need to find G 2008, and we know that we can write this as G3 plus 2005. Its period is 1, so it'll be equal to G3, and G3 is F3 minus 3 plus 1, and F3 is 1. So value of G 2008 is minus 1, and that is the answer to this question.